Hello, everyone. Thank you very much for your interest in statistical analysis using Python. If you are a regular viewer of my channel, you know that I have covered topics of image analysis primarily and data analysis using machine learning and deep learning. But with these series, with this specific series, like a series of at least 5 to 10 different videos, I would like to provide you a quick introduction, sometimes in-depth introduction to statistics, which is timeless, I should say. I mean, machine learning and deep learning, every day there is some new algorithm. Great, we are advancing in the right direction. But the core essence when it comes to data analysis, you cannot live without statistical analysis if you really want to analyze data. Whether you end up using data science or machine learning, that's a different point, but you need to understand data first before picking the right tool for data analysis. So the whole point of this series is to provide you an introduction to various statistical tools, with the first video, this one, being the core basics. And I'm doing this after interacting with various researchers and engineers and others who want to become data scientists. And one thing I learned is you need a refresher in statistical analysis. I need a refresher in statistical analysis all the time. So I hope you will find this series of videos to be useful. And before I talk way too much, let me go ahead and jump in and let's explore this quick tutorial. When I say quick, normally my videos are 45 minutes long. This, I hope, will be much shorter than that. And every video is going to be focused on a specific learning topic. This obviously is going to be a quick introduction and understanding the core metrics. Okay, and of course, as usual, if you haven't, I should request that you pause the video right now and subscribe if you haven't already subscribed. And also down there, when you're trying to subscribe, right next to it is a little thanks button if you're feeling extra generous. Let's go ahead and jump in. I don't want to make this a boring PowerPoint presentation, although it's going to be for the next few minutes, a few slides to provide the background. And after that, we'll jump into Python code as usual. And the link to that code, you'll find that down in the description. Okay, first of all, what is statistical analysis? Well, it's the definition, the textbook definition is it's the science of collecting data, exploring data, and presenting the data so that you can discover the underlying insights like patterns and gain some insights about your data. Using statistical analysis, you describe the characteristics of your data. What is the basic characteristics would be, what is mean, what is standard deviation, right? We'll go through all of that as we go through this series. You come up with some hypothesis and you test hypothesis about populations. You have one set of data, another set of data. Are two different, or are those two same? You come up with some hypothesis like, okay, they are the same until you uncover any differences between them. This is the basic concept of t-test, which we will again cover in the next tutorial. It quantifies the relationship between different variables that you have in your data set. And at the end of the day, it provides a framework so you can use evidence-based or make evidence-based decisions. Rather than just saying, oh, I saw some difference in the data, you can show why you saw difference in your data. So why do you want to perform statistical analysis? Well, obviously, as discussed earlier, you want to extract meaningful insights from your data so you can take some action about whatever the data is trying to convey. And that's what the second bullet point here is: make data-driven decisions with confidence. Otherwise, you're like, okay, without validating your hypothesis, how do you make any decisions, right? So statistical analysis helps you with that and quantify uncertainty in your findings. Okay, obviously every data, when you make any decision, there is some uncertainty associated with it, and statistical analysis allows you to quantify that uncertainty. You can say I'm 90% confident, yeah, after doing your analysis. And as mentioned earlier, you validate your hypothesis and whatever assumptions you have about the data or about this scenario under which the data has been gathered. And finally, the most important, we all communicate with our managers and their managers, and sometimes managers to manage, they're like 3 levels up. And each level that you go up, the more important it becomes for you to use visual statistical tools like plots to convey the meaning, because no one has, as you go up, they don't have a lot of time to understand they don't even need to know every little detail. So just show a plot showing that, hey, we need to probably invest in this because of this plot, whatever the insights are, right? So visualization is also very important, that I'm going to cover. And all of this we're going to use Python to achieve, or to work with our data. Okay, now there are various types of statistical methods, like the top 3. I mean, basically, descriptive statistics is something that you probably hear all the time. And it, as the name suggests, it summarizes and describes data characteristics. Well, what does that mean? For example, a teacher calculates the average test score of her class to summarize the overall performance, right? So what is the average? So it's descriptive statistics. Inference statistics, again, as the name suggests, draws conclusions about populations of samples. You have different populations of these samples. For example, a pharma company. They may be testing a new drug on different populations, and you want to infer or extract insights about its effectiveness on these populations. So before rolling out to the general public, they need to understand exactly what the implications are, and inference statistics definitely helps there, right? Predictive statistics, again, as the name suggests, use the current data, historical data, to predict future. And that could be financial analysis, or an e-commerce company is trying to forecast what they would, what type of targets they will be achieving next quarter based on what they have done, or based on the patterns that they saw by analyzing past and current data. And there are various tests that you perform as part of statistical analysis, like parametric versus non-parametric tests. Parametric tests, again, it assumes normal distribution, like the bell curve, right? So it assumes that, okay, you have a bell curve, and to perform parametric tests, there are a few other specific conditions depending upon exactly what test you're performing. We'll learn about all of these in this series. And parametric tests are more powerful when these assumptions are met. Like when you perform a t-test, for example, if the data is distributed normally, of course they are more reliable, they are more powerful when you have those assumptions met. Otherwise, you may have to use non-parametric tests. And like I already mentioned, t-test, ANOVA, Pearson correlation, these are some of the examples of the parametric tests. And when would you use that? Well, let's say you're comparing average cholesterol levels between 2 treatment groups at a medical clinic, and when the data is normally distributed, you perform t-test to see is the effect on these two, cholesterol levels between these two groups statistically significant or not. So that's a good example. Again, we'll go through certain examples. In this tutorial, we are going to use a similar data set. I'll get to that in a minute. Now, what falls into non-parametric test is you have very few assumptions about the data distribution. You don't know how the data is distributed. It's not normal distribution. In a way, think of this as, I think I put the bullet point, uses ranks rather than actual values, which means, is it like category 1, rank 2, rank 3, rank 4? So in these scenarios, non-parametric tests actually help. And again, as we go through this series, you'll learn more about what these bullet points actually mean. A few examples of algorithms would be Mann-Whitney is probably, and Spearman correlation is something that you may have heard before. And a real life scenario is you're getting I think the example here is customer satisfaction rating, 1 to 5 stars, and you have your product. You ask customers to kind of give you, these type of ratings, and to analyze, these ratings that are not, that do not fall into a bell curve, right? That's not normal distribution. You need non-parametric tests to make sure whether the tests, whether there is a difference between different groups. Okay, now which statistical test are you going to use? Again, it comes down to what insights you're trying to gain from the data, right? So every time when you get a new data set, at least I sit down and think about, okay, what do I need to do? I'm talking about any data. This can be image data, this can be structural data, financial data, your accounting, your forecasting. It doesn't matter. The key question is, for example, you get a whole bunch of data about your customers all over the world, and the question can be, who are the top customers who buy our products? How often do they purchase? Are they returning customers? And are they purchasing low value products, or are they purchasing high value products? If it is low value products, is it just one time and done, right? So there's so many questions that you can ask of your data so that you can make some sort of a business decision. The business decision can be, okay, I need a key account manager for a specific company, right? Or a specific group of companies, a type of companies. Okay, oil and gas, for example. A specific type of customer, they repeatedly purchase and repeatedly purchase high value products. Then you can come up with a strategy about how to get more such customers, how to take care of existing customers. So there are actions that you perform based on the questions that you're trying to answer here. So the questions can range from, I already mentioned about the questions, but how many groups are you comparing, for example, right? If you have like two sets of groups that you're actually comparing, then t-test, a regular t-test may work. But if you have 3, 4, 5 different groups, for example, you have a whole bunch of pathology images. Let's say, I'm just thinking out loud, showing you benign tissue. And you have stage 1, stage 2, stage 3, stage 4, like different stages of cancer, for example, different tissues. Now you're trying to compare nuclei sizes of all these 4 or 5 different tissues. Then a t-test, regular t-test, is not useful because you're not comparing 2 populations, you're comparing multiple populations. So you may need a different approach for that specific scenario. So choosing the right statistical test is it's always important. Again, you learn by example as we go through this series. We'll get to answer all of these. Okay, I should have animated this this slide, but basically choosing the right statistical test. There are, as I already mentioned, you think about what are the population. Is it 2 groups, or is it 3 or more groups? If it is 2 populations, is it parametric test that you're trying to perform, or is it like non-parametric type? Of course, the data itself dictates which one you have to pick. And if it is parametric, then of course a t-test, independent t-test is what you can actually use, a paired t-test or an f-test. And non-parametric, as you can read from the screen, I don't want to read every little thing. And when you're comparing 3 or more, ANOVA is the common one, at least that I have used. And non-parametric also you have, you can read it from the screen. So there are specific tests, statistical tests, depending upon what type of data you have, and including how many, what's the populations that you're trying to compare. And now, obviously, at the end of the day, this tutorial is about using Python, but I am providing you the background in statistics so we can go ahead in Python to use the right library that contains these. In fact, when I took my statistical analysis courses, there was no Python. I'm talking about late 1990s. And the design of experiments, we had to manually calculate. Of course, we had graphing calculators and all that, but manually hand calculate. And that's the best way of actually understanding a specific algorithm, even if it's mean or median or variance. When you do it by hand, you get much better appreciation. So I definitely recommend if you can. But luckily now we have Python libraries that can help us in making this process easy, as long as you understand the fundamentals. You can't just use the library and then report the results, because you need to interpret the results. And when you're presenting this to your bosses or whoever, when they ask a specific question, you need to be in a position to answer that specific question, right? You can't just blindly give the data. And that's the whole point of this series. So you understand this at least to a certain depth. The core libraries that I'm pretty sure most of you know are NumPy, SciPy, Pandas, right? These are regular libraries that you probably have already some exposure to. On top of that, stats models is a good statistical models and test library. Scikit-learn is something I hope my regular viewers know, because I use this quite a bit for machine learning, like whether it is using gradient boosting or, but those are machine learning, but scikit-learn also use some statistical tools. And the next matplotlib for plotting. And then there is another one, penguin. I don't know how to say that. Struggle all the time, but that's a user-friendly statistical package that we probably will use again, may not be in this tutorial, but in the next couple of ones. Okay, the data set I'm going to use for this tutorial when we jump into Python is the UCI heart disease data set. Again, I used this a long time ago in one of my early videos. I guess I have now 400 plus videos, and I did this a long time ago, but a quick refresher. This is a medical data set with 303 patients, and it has 14 attributes or features, if you want to call that, or 14 columns, including what the demographic is, the clinical and laboratory features, and the target variable, which means the variable that you are predicting is whether there is presence of heart disease or absence of heart disease, like 0 or 1. 0 means there is no heart disease, 1 means there is heart disease, right? So that's the target variable. And mix of categorical and continuous variables, meaning you have some variables with some just numbers and some variables with values of 0 or 1 or 2, or in fact, it may not be number. It may be true or false. It may be yes or no, right? So it could be in plain English. So these are categorical columns. And when you wrangle the data, when you clean up the data, sometimes for better visualization, it's recommended to encode this data if it's categorical into zeros and ones, or 0, 1, 2, 3, whatever the categorical values are. Okay, so you can read more about this data set by following the link that you see. A quick Google search for UCI heart disease would definitely get you there. Now, let's cover a couple more slides, like understanding descriptive statistics. Like here, as you can see in Python, we just type, for example, hard data. Once you read the data in, .describe. As you can see here, it says .describe, and it gives you something like this, right? It gives you count, mean, standard deviation, minimum, 25, 50, 75, max. I hope most of you know what these are. The count is nothing but, did I put that down here? I mean, this is a pandas function, obviously. So I say obviously, but it's not obvious here. It's a pandas function, which means heart underscore data is a pandas data frame, and it's describing the data frame. That's what that describe actually does in coding. And of course, it provides a summary of the central tendency and dispersion measures. What that means is central tendency, mean. What is the mean value? We have total 303 entries. Of those, the mean is 54.43 here for age. Average age, mean age is 54. The standard deviation, plus or minus, is 9. That's the standard deviation. And minimum age is 29, and maximum age is 77. And I hope you know all these. And I think on the screen I explained, I don't know why I'm not showing you and then just explaining. The percentiles like 25, 50, 75 is probably something that you may or may not know. These are values that divide this into quartiles, which basically means if you plot this data, again, normal distribution, right? A bell curve. And the median is the 50th percentile, somewhere in the middle. Mean is mean of all values. It may not be exactly in the middle, but mean is the mean average of all values. 25th percentile means 25% of the data falls below that value. 50th percentile means 50% of values fall below, of data points fall below that value. By definition, that is the median, right? So when you organize, for example, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then you find the median value, and then 50% of those fall below that median, and 50% are above that median value, right? And 75th percentile obviously means 75% of the data falls below that specific value. In real life scenario, if 75th percentile, it's also called Q3, represented by Q3. If, for example, if it shows a cholesterol level of 274, what does that mean? That means 75% of patients have cholesterol levels below 274 and 25% of them have a cholesterol above that value. I know these could be basics to some of you, but again, this can be a good refresher if you haven't thought about this in a long time. Now, plotting, visualizing is one of the key aspects when it comes to statistics, because not only to convince yourself, but also to convince others. It's very easy way of showing the data and saying, for example, on the left-hand side, I believe this parameter is nothing but the heart rate. I forgot what exactly that corresponds to. I have to look at the data set, but we'll do that later. But based on this, whatever this parameter is, I think this is the heartbeat when they exercise or something. But whatever it is, it's heartbeat. Let's say the heart rate, and the green, which is with heart disease, it is showing slightly lower median value compared to the 0, right? With the people with no heart disease. So visually, you can say the green one is slightly to the left and the bluish one is slightly to the right. Now, are they statistically different? We need to run a test, a t-test or something, which we'll do in the next tutorial. But visually, you can tell that there is a slight difference. But it's very important to back your intuition that green is lower than blue, to back it up with real statistical uncertainty values. Yeah. Again, we'll do student t-test with p-values in the next tutorial. I'll explain what those are if you don't already know, of course, in the next one. So please do subscribe if you haven't already done so. On the right-hand side, you're seeing these box plots, and these box plots are very common. You'll see this in financial and also in bio analysis quite often, and also in materials analysis. When I was doing my PhD, I had to run a whole bunch of samples and then make sure that whatever the findings that I'm reporting are statistically relevant. So the box actually represents, on the left-hand side in this specific example, the box on the left-hand side shows the box itself, right? This is for 0, which means no heart disease. So all this data corresponds to no heart disease. All the data on the right-hand side corresponds to yes, with the data sets that are tagged as yes, they got heart disease. And within the box, you'll have 50% of the data. The box itself represents 50% of the data for that specific group. And the top and the bottom, like these two edges, they show the low and high end in your data, except for outliers. All of these bubbles that you see outside, all these bubbles, that tells you the data that falls outside of, that are outliers, basically. So just to summarize, and the central line, I believe, is the median value. Yeah, so you have a box and you have a central line right there. 50% of data falls in within this box, and this is the lower end. This is the high end value. All the other ones are outliers. That's a quick summary of these box plots. Now, before jumping into code, one final thing, it's very common to actually look at correlation matrix when you have a lot of parameters, a lot of, you can call them attributes, for example, and the correlation matrix is pretty easy to understand. In this graphic, it's going from dark blue to dark red. Blue, as you can see, is negative correlation. Red is positive correlation, meaning of course, this value is correlated to itself. That's why it's showing you very strong positive correlation. But if you look at this reddish area, 0.38, where whatever that CP is correlating with EXANG parameter, it shows that, okay, so there is a 0.38 positive correlation, meaning whenever this goes up, the other one goes up by that much. That's basically what, on average. That's the positive correlation. Negative correlation is when age goes up. In this case, the heart rate apparently is going down, which makes sense. You have a lower heart rate as the age actually goes. So that's negative correlation, which is also important. And you can easily draw these correlation matrices with just a line of code in Python. All of this stuff is very easy in Python. So let's go ahead and jump into our code. And as usual, I am showing you the code in Colab, in Google Colab. So if you have a Google account, obviously you should be able to access Colab and practice, whatever you're seeing right now. Okay, let's go ahead and start. It's pretty straightforward. Like I mentioned in one of the last slides, there are certain libraries that we typically work with: pandas, numpy, and matplotlib. Pandas to actually handle the data in a structured format, and numpy, of course, for numpy arrays. So the calculations become easy in case you want to do that. And matplotlib for plotting. And seaborn is something I did not mention earlier, but I love seaborn for plotting when it comes to statistical analysis. And plotly is another library. I don't want to get into that, but if you know how to use plotly, it helps you in generating interactive plots. But seaborn gives you better styling, and that's exactly what I did in the next block here, which is I define the figure size and what type of style I want to set for seaborn. You don't have to do this, but it keeps all the plots, clean, let's say, and uniform. And let me also run the visualization style. So now, what data? The UCI heart disease dataset, you can go ahead and Google search, or here is the direct link to it. And I am assigning column names as age and sex. And where did I get this? I got this from their documentation. Why am I assigning this? Normally, if you read directly from CSV file, pandas automatically recognizes the column names and assigns them. But if I click on this, it opens up this data. This is nothing but a CSV type of data set, and they do not have any column names. If I zoom in, it starts with data. The first one is age, and the second one is whatever I have it down here. Yeah, is it a male or a female? So the values are 1 or 0 right there. So that's how they kind of defined male or female, and so on. Okay, so these are the column names, and I'm reading it using pandas, and I'm just doing hard-data.head, and it gives you the top 5 data values. And you can actually say how many you want to see, but this gives you a quick, I'm showing you how I work with this data and how I recommend you work with this. First, get a good idea of what the data looks like. Yeah, so age and your sex or gender, if you want to call that, and all the other ones. And please understand what these means. Like, for example, cholesterol level is straightforward. And this one is, I know this is heart rate, but I forgot exactly when they collect this heart rate. I think this is when they're exercising. I may have added that in the notes somewhere. And, or this one is basically that. Okay, so this gives you a good initial overview of your data. And the next thing is you want to get more information about your data, and your whatever the pandas data frame name is, .info gives you the basic data set information, which is what is the column, what's the column name, and how many non-null count you have. Here you see there are only 299, which means there are 4 null entries, meaning there is nothing there in those cells. We need to either drop them or fill them with some values, which we'll see in a minute. And what type of data is it? In all cases, it's float 64, except for the target, which is an integer. And the target is 0 or 1. Is it no heart disease or yes heart disease, right? So that's what that target is. Age, excuse me, should also have been integer, but it's okay. We can work with float. Okay, so this again gives you a nice understanding, summary of the data. Again, very important for you as a data analysis expert, data scientist, data whatever you want to call yourself. And now the next thing is how much of our data is null. Like, of course, we should see some of the null ones right there. Most data is complete, except whatever the calcium values, I guess. I don't know, CA is 4, and we have 4 missing, and here we have 2 missing. That's not much. You can either drop them, or we don't have a lot of data. So instead of dropping them, we can fill them with some value. You can fill them with a mean value or a median value. I try to stay away from mean because you always have some outliers. So fill that with a median value. And how do you do that? It's basically .fill NA, fill it with median, So it fills these with median values. Now, if you run this again, it will show all zeros. Yeah, if you run the same command. Okay. Now, the next thing we're going to do is do dot describe. I already talked about it in the slide, presentation part of it. It gives you the count, mean, standard deviation, minimum, and the different quartiles right there. And another note, people sometimes refer certain part of the data as interquartile range, IQR. IQR is something sometimes people report. That's nothing but Q3 minus Q1. So the region between Q3 and Q1, which is basically, it represents the middle 50% of your data. When I say middle 50% of your data, that means whatever the data you're looking at, whether it is age, for example, age, let's say, or heart rate, you arrange that data from lowest to highest. You arrange that from lowest to highest, whether it is age or heart, whatever the data you're looking at. And then you look at the middle 50%. That's what this means. Okay, I hope I'm not explaining way too basics, but you never know where someone has a gap in their knowledge. So I tend to, cover even if it's basic. Okay, for our data set, let's go ahead and dot describe. And it should give us all you already saw this in the PowerPoint presentation, exactly the same thing. We have 303, and of those, the mean age is 54, and you can see all the other ones. Yeah, it doesn't make sense to actually look at the mean and standard deviation of the sex because it's either male or female in this case, right? So it's not continuum. So there is no point in looking at that, even though it prints it out. So you have to know exactly what the implications are. Or what a given attribute actually means, and does mean standard deviation make sense in that, or not just mean standard deviation, does a specific statistical value makes any sense for that specific attribute. Okay, with that, let's move on to the basic data visualization. In fact, I will, in the next tutorial, go a little bit in fact, I don't want to say detail. I'll explain what mean is and what standard deviation is from an equation point of view. Mean is basically taking all the values and dividing by total number. Standard deviation is you take that mean and from each value subtract that and do something. I'll explain that in the next tutorial if you don't already know. But don't think next tutorial is a waste of time because I'm explaining those. Those are only the two aspects of a few other things that I'm going to explain. Yeah, because I don't want to leave anything to your assumption. Okay, now data visualization is very important. Again, I'm not going to explain exact every line by line, but here what I'm doing is taking the target, which is zeros and ones, right? So is it heart disease? Is it no heart disease? And then I'm applying a lambda function saying that, hey, if x equals to 0, value, I don't think I need this because they are already x equals to 0 or 1. But if you look at the next one, I'm changing this for better interpretability. In this case, I'm doing the reverse, which is I'm taking 0 and I'm saying if it is 0, it's female. If it's 1, it's male. So when we print it on plots, it makes more sense than 0 and 1. Again, very basic stuff right there. And this part of it is basically within Seaborn, I'm using histogram plot to actually look at the distribution of the heart disease data set. Let's go ahead and plot it. Again, this is something you saw earlier, and there you go, right? So I like Seaborn for one other reason. Obviously, the visualization is great right there. And on top of this histogram, I obviously enabled the KDE equals to true, if I can find that line again. Yeah, I put KDE, kernel density estimate. That's basically this line right there. While the box plot, the histogram plot shows you discrete values. This one kind of puts a continuous, spin to it. So you can easily interpret what's going on. It's almost like there's a peak right here and another major peak right there, right? So it's like a Gaussian peak right here, if you fit it, and another peak right around there. Yeah. So there's a lot you can learn from here. And again, you can see, of course, mean is very rarely equal to median. So you can see the difference between those two. And you can get good idea of what's going on. Like age, of course, bulk of them are centered around like slightly less than 60, like around 57, 58. And there is another peak in your data for age around 45-ish right here. Immediate insights. Okay, now let's do a box plot. Yeah, for cholesterol by target. So cholesterol levels by, this is the cholesterol column that we are actually, remember, there is a column with name CHOL. That's exactly what we are plotting, but we are plotting a box plot instead of a histogram plot, because this gives you better insights in this specific case. Let me zoom out a little. I zoomed in so you can see it, but the plots are being too zoomed in. Okay. So heart disease present, 0 equals to no, 1 equals to yes. And this is no heart disease, this is yes heart disease. And again, this is the lower limit and this is the higher limit. And these are all outliers. There is one that's cholesterol of 500 plus. That's, I feel bad for that person, but that's very high cholesterol. That's a complete outlier. Basically, it doesn't mean that that person doesn't exist. It's just that that's so outlier, it doesn't describe the general population. Yeah, so anyway, I think we went through this. Now, if you ask me a question about, okay, so is the cholesterol different between patients with heart disease and without heart disease, then visually I can tell you this box is slightly higher than the other box. This is why you need your parametric tests to compare these two populations and say whether they're statistically different or not. We'll do that again in the next tutorial. Okay, now let's do a count plot of whether it is a male or female versus the disease status. So this again, there are various questions. In this case, the question I'm asking is there more heart disease in male versus the female, right? So if you look at the population, more males in this case show heart disease compared to no heart disease. Opposite for the females. More females do not have heart disease compared to the males, right there. Of course, we have more male data compared to female data, but still, if you look at the relative, it's different between male and female. So that's an immediate insight that you got literally by looking at the plot. Again, is this statistically different? Obviously, visually, I can see how big of an effect it is. So I know when I perform a quantitative test, I will get a value that tells me that this effect is real. Okay, and the next one, finally, correlation map, which is as simple as you take all your numerical columns from your heart data and then just dot CORR. So this is part of your pandas. So go ahead and run this. And not much to explain when it comes to code, actually. It's very straightforward. There is a specific method that's predefined as part of this, whatever the library you're using, and you're just calling that. But you need to understand what that actually means, right? And again, this is exactly what we have seen earlier, so nothing to describe there. And finally, before ending, I just want to make sure you understand what's going to happen in the next few tutorials. The next one, we're going to look at descriptive statistics, a little bit in depth, like, okay, measuring the central tendency. Again, that means mean, median, mode, and dispersion of this data, which means variance and standard deviation, and data visualization. Of course, we'll use more histograms, and later on we'll look at normal versus non-normal distribution and testing for normality, because how do you know it's normal? Well, visually you can kind of see, but is it really normal distributed? So you can perform certain tests on the data set to understand if it's normal or not, and then you can actually transform data possibly to make it behave normal, let's say. That's one reason, like log transformation is one example I can think of right now, but this is something we will cover. And of course, parametric tests like t-test and non-parametrics and advanced correlation analysis and all the other details. So I seriously hope you stay. I mean, if you're at this point of my video, I hope you are finding this to be very informative. So I really hope to see you in the next tutorial. Thank you.